In the previous class, we looked at USB systems. I will briefly mention something about disk subsystems in this class and a few issues relating to how we can mix and match different types of devices. I think in disk systems, there are varieties of them you can see. One is called the direct attached storage. What is this? This is a typical PC kind of situation. In a PC, you have a disk attached to the bus, PCI bus, and this is what is called direct attached storage. But of course, in larger systems, you will have many more disks attached to the same bus. Okay. For example, even on your PC, typically you can put in about easily 2 disks or 4 disks. You can easily do it. Okay. If you want to put more than that, you need some additional hardware to be able to do such a thing, because usually space is not available and you might need what is called enclosures, external enclosures. Okay. So, basically direct attached storage means it is the storage is more or less connected electrically through some buses and it is very near the CPU itself. Okay. You can also have what is network attached storage, what is called NAS. This is the one which uses what is called a file protocol. What does a file protocol mean? It means that you are the CPU or the processing side knows about file names and it asks to the NAS system saying that please give me this particular file, etc., etc. Okay. So, these are the file level, the protocol is at a file level. There is also something called a storage area network storage, and these are what is called the block level. Here the requesters will only ask in terms of block numbers, not file. Typically a file is composed of many blocks. So, a storage network basically it is accessing things at the block level, not at the file level, but this one is accessing at the file level. Okay. So, essentially if you look at it, you might see the following. Okay. In the case of these are the what let us call the CPU, right, and this is the let us say the NAS. Then here you will only ask what files. Okay. Everything is in terms of files and somebody has to map it here from files to blocks or whatever, the way it has to. But the CPU does not know anything about the block structure, it knows only about file names. Now, the other one, this is basically the NAS system. In the case of SAN kind of system, this is at the block level. Okay. So, there are plus and minus points for both of these things. This one is somewhat simple, basically because most essentially CPUs, most of the CPUs, right, most of the operating systems, let us call it, instead of CPU I should call it operating system actually. Most of the operating systems have file systems that come part with it. So, basically the file system basically what is happening is the file system is now composed of 2 parts, what is called a client on this side and then a server on this side. Okay. So, for example, we have a system called NFS, network file system. There is a client NFS portion on this side and the server NFS on this side. The client NFS takes care of all the aspects relating to issuing the request, and the server NFS, it figures out, given the file name, or actually what is called a handle. Okay. Basically, there is a conversion between file to handle that happens. In the beginning, you give a file name, and then the NAS system gives you a handle, and then later on you can use the handle as a way to talk about that particular file. Okay. So, to make it more accurate, it is file or handle. Okay. That is how these two interactions are. Here in this case, it is strictly block level. Okay. That means that this particular OS actually should keep the maps about where the blocks are. It's the responsibility of this particular OS/file system. Okay, there's a file system out here, and it is their responsibility on this side to figure out where the blocks are. Okay, so that allows for careful management of the resources, but it's more work on this side, and it also turns out, since it is even lower in the layering, okay, this SAN does not have any idea about how these blocks are being used, because it doesn't even know that a file is there. Basically, a file is composed of many blocks. SAN has no idea about which blocks are actually part of one single file. Whereas here, the NAS knows which files have which blocks. So it's more information on this side. So NAS can do something slightly more intelligent here, whereas SAN might not be able to do that much here with respect to where the blocks are in which files, etc. Okay, because all that mapping is kept by here. So in a sense, there is more intelligence on this side, and these have to be geared for some other types of operation which emphasizes its capabilities better, not at the level of intelligence about where the blocks are in which files. Okay. You also have something called distributed storage. Basically, if you look at Google file system, they don't use either of these things. Okay, they use a distributed storage. In this model, what we are talking about is you have multiple nodes, each of them have some storage. Okay, okay, let's call this some storage. Okay, and a client, there could be many clients. This could be clients. Okay, and they basically go through what is called a metadata server. Let's call it M. They first talk to the metadata saying that I'm interested in some piece of information, and the metadata says your information is present here, 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 and then the clients will directly talk to these guys now after that. They don't go to the metadata. Okay, that means that initially the storage is distributed across many nodes, and the metadata keeps the information about where they are. The clients have to contact the metadata to figure out where things are first. Afterward, they can directly access them. Okay, this turns out to be very scalable. That's why the Google file system, which we'll talk later, uses this model. Of course, there are many models, but this is a good example of that. Okay, distributed storage. Now, with that introduction, let's look at a disk. First thing important about is that a disk is an electromechanical component. This is different from what we looked at before, the flash, which is a semiconductor based technology. This is a electromechanical, and basically there is both electrical aspect and magnetic aspect in the system. Okay, so if you take a disk of late 2010, it is 5400 RPM, revolutions per minute. It's making 5400 revolutions per minute. So you can think of it per second. How much is it making? You can divide it by 60. How much is that? It's about 90 revolutions per second. It's spinning quite fast. Okay, and it's got what is called as average seek of 12 milliseconds. That means that if you have a disk and you go from half the distance on the disk, okay, your head is, let's look at the picture again. If you look at a disk, it has got some concentric tracks. Okay, these are called tracks. Okay, and your head can be from anywhere here all the way to outside. So the average half distance, okay, any half distance, okay, from here to here, wherever, okay, from here to here, that is usually given by the term average seek time. Okay, half. Okay, an average you could be anywhere, right, and you want to reach any other place. On average, you have to do half the number of tracks you have to cross. Okay. So that's basically what is the 12 milliseconds. Okay. What is called full stroke means you go from one extreme end to the other extreme end. That's full stroke, the 20 milliseconds. Okay. There are of course some minor differences. Actually, it turns out read takes slightly lesser than write, for example. For example, in this disk, write takes 13 milliseconds, doesn't take 12, okay, because it has to, writing is a slightly more involved operation. So for that reason, it takes 1 extra millisecond. Other important thing that is interesting for us is, you will see that there is a number of bits per square inch. Now in this disk of 2010, it was 375 gigabits per square inch. That is, you take 1 square inch, you are packing in about 375 gigabits. Nowadays you have terabit per square inch. Okay. People are saying that beyond that is going to be tough, okay, but there are other new technologies that are coming in which will probably give you packet even better. Okay. So you can just remember it as 1/3 of a terabit per square inch approximately, 1/3 of a terabit, but currently already you have terabit per inch square. With respect to the throughput, okay, you can get about to and from media. Now inside the disk, not only is the magnetic medium there, there is also some electrical buffers made with semiconductor memory. So normally what happens is that you are on a bus, you transmit to the electrical component first, and from the electrical component you get to the magnetic medium. That's why we are talking about from buffer inside the disk to the media, that's magnetic media, and vice back and forth. That's about 875 megabit per second. But if you are talking from the CPU side, which is coming from the, typically from the electrical side, and then you can talk to the electrical buffers, okay, semiconductor buffers, electrical buffers, whatever you might call it, okay, that one is much higher. Okay. Basically the media is the bottleneck, the magnetic media, okay, that is coming, that you can do it only 875, whereas if it is only electrical to electrical kind of transfers, you are doing about almost close to 4 times faster, 3 to 3.5 times faster. Okay. Now again, this is what is called a block-based device. Its typical sector size is 512 bytes, block size is 4 kilobytes typically. Again, as we discussed last time, in Google file system the block size is 64 megabytes, so that you can get effective throughput. Nowadays the sector size for a long time has been 512 bytes. Nowadays since 2010 you are getting newer devices with 4 kilobyte sectors. Of course most people still use it as 512 byte things only, but basically why are we going for higher sector size? Just like the way we went from 4 kilobyte to 64 megabyte for Google file systems, it turns out there are reasons why people want to go with higher sector size. It turns out it reduces what is called error correcting code overhead. To give an example, if you take 512 byte sector size, you need about 40 bytes of ECC, read Solomon code. Okay, it's almost talking about 40 by 512, it's about 12% approximately. Okay, you lose 12% just in the ECC overhead. Whereas if you go from 512 byte to 4 kilobyte, it turns out you need only 100 bytes. Okay, so since you are going only 100 bytes, you are losing about 4%. Okay, the efficiency in this case 4 kilobyte is 96%, in this case around 88% or 87%. Okay. The reason is that the amount of ECC read Solomon code you require is not linearly proportional to the size of it actually turns out that with slightly larger ECC size you can do much better, you can handle bigger sized sectors. Okay. It was another thing that does is it's something called intersector gap overhead. Basically if you look at a track, every sector, after the completion of every sector, there is some markers, okay, so that you can position the head. Okay, you need to know where the sector ends and where the sector begins. So the thing is, there is some specific markers on the disk, and that is usually that is where the intersector gap is. Okay. So, the more number of sectors, the more gap has to be kept. Okay. So, that also eats into the space. So, if you go with bigger sector size, it turns out to reduce that overhead also. Okay. Again, I think some of you all must have looked at all these things. There in the disk, we have something called heads, tracks and cylinders. Now, these are all turns out to be logical concepts only, because physically they are oftentimes different. The reason why it has happened is because in very old disks, 1980s approximately, you had in the BIOS, for example, there were fixed number of bits for heads and tracks and cylinders. For example, there were something like 4 bits for the number of heads, etc. Okay. And it turned out that because of the fixed size, they could not access more than something like 500 megabytes in the beginning, sometime in the 1980s. So, they reinterpreted these bits as in some different ways, so that even if you had only 2 heads, you still call it 16 heads and still work with it. Okay. So, for example, on this disk, it says that there are 16 heads, 63 tracks and so many cylinders. It's completely, let us say, does not correspond with reality. It turns out this particular disk has actually only 2 physical heads, only 2 physical heads. Okay. And you can look at the number of cylinders, that also is way off. Okay. Basically, it has, if you look at it, it has got 172,675 cylinders. Okay. It's about 10 times as much as this. It claims that it has got 16,383, but actually it's got 17,267, something like that. Okay. And basically what has happened is that heads has, when it's 2, it is reporting as 16, and it is compensated by going with larger number of, smaller number of cylinders when there are actually more number of cylinders. So, if you multiply all these things, it is the same number of bits, okay, in terms of the size, something like that. Basically, the number of bits have been reused in a different way. So, that is why there are logical concepts, physically they are different. What is also interesting about this is that it is the number of bytes on each track is different. Okay. I think as you can imagine, if you look at this picture, for example, right, this area is, this linear dimension is quite different from this linear dimension. Okay. This is much bigger than this one. So, if you are going to have constant density, okay, there should be more bits here than on that track than on this track. Okay. Now, this is in the past, in the very early devices, they somehow did not like that. So, they would actually have the same number of bits whether here or here, by making the bits slightly less frequent outside and keeping the density that they wanted inside. But nowadays, they do not want to lose the density. So, there are many more bits outside than inside. Okay. You will see that it has been categorized into multiple zones, zone 0, zone 1, 2, 3, 4 up to 23. So, there are 24 zones. On this particular disk I am talking about, there are 24 zones. The first 0 to 7153 cylinders have 1920 sectors. This is the outermost. Essentially, you have almost a megabyte on each track, on the outermost. But if you go in between, you will find that it reduces, it is going to be 720 kilobytes. And once you come to the innermost zone, okay, you will find that it has got this number of cylinders, it has got 912 sectors, only about half a megabyte. So, innermost only half a megabyte. Okay. So, now it turns out that this is all this is highly device specific. So, when you are talking about file systems, they do not want to know about all these things, because that means that for every disk that they see, they have to configure the algorithms again. So, they do not really worry about all these things. They just assume that a disk is bunch of sectors, and they do not worry about usually the track or cylinders, etc. They just do not worry about all those things. They say my design should be robust to however these things are divided. But some file systems actually do take some of this into account. If you look at the well known fast file system FFS, which is there also in Linux as ext2 file system and ext3 file system, they actually try to allocate blocks in nearby cylinders. They may not take into account the track size per se, but they will worry about the fact that you should be near whatever blocks for a particular file is being allocated, they should be on nearby cylinders. Okay. That way they will access time for when you want to move from one block in one cylinder to the next block, which happens to be in the next cylinder, the amount of movement of the head can be minimized. Okay. So the basic problem of what we are facing is the upper level software doesn't want to go into too many of these details. So once it gets too much into details, then it means that it is highly specific to that disk. That means that I cannot take some other disk and install, put this one, right? It makes it difficult. So they had to be slightly abstract away some of the details. So some file systems just say that my abstraction is only blocks. Some other file systems will say that at least I will think about it in terms of cylinders, but I will not think in terms of tracks and other things. Okay. So that's a brief introduction to the disk issue. Let's look at tape. Here tape is nowadays not that very common. It used to be common about 20 years back, because we used to also use it to store our things, but nowadays disk has replaced tape, okay, for storing things. Okay. The thing about tape is that it is used now only in very high end systems. For example, if you talk to people in CERN, the people who did that Bose bosons, right, who are discovering some new types of bosons, you might have heard about in some atomic nuclear facility, right, research facility. So they generate so much data that anything they have to back up, they can't afford to back it up in disk, it's too costly. A tape is about a factor of about 3-4 times cheaper. So tape is being used in very high installations, but in regular installations what we normally use, tape has disappeared. Okay. It's only for very large capacity systems, very large capacity, petabytes, hundreds of petabytes. Okay. The problem with tape is that it has got a very high latency. Normally the latency is in terms of minutes. Sometimes it can even be half an hour, because somebody has to physically go get the tape and install it on the device, and so you have to call somebody and the person has to move physically and go and get it. Okay. The only important thing about tape is that it's got a very high bandwidth. Once it starts moving, it moves at very high speed. It can be some of the high speed tapes, they can have better bandwidth than even disks. Okay. They are very good at bandwidth. That means that the minute you start it, if you want to write a huge chunk, okay, it can write it quite efficiently. But you can't afford to stop it and rewind all those things. If you do that, you are dead. You don't have efficiency. So it's only used for backup. Okay. Also the thing is, because of all the controller cost also is very high. Basically these are very big systems, so the electronics that controls these things is very costly. Okay. So we will not be discussing tape in this particular course that much, but I want you to be aware that tape is a viable medium still, because this is a very low cost for extremely large capacity storage. Okay. Now we've already seen 3 types of technologies: flash, disk and tape. Okay. Flash is semiconductor persistent memory. What is the capacity? What is the characteristics? Its capacity is low compared to disk, for example. Access time is low compared to disk. Cost is high compared to disk. If you look at a disk or tape, it's a magnetic persistent memory. Capacity is very high compared to flash. Here we talk about access time, here we talk about latency time, because it can involve seeking also. Okay. So here is just, there's hardly any seek or any such things, you don't have those aspects here. But here we have not only the access time, but also the seek and rotational latencies. And the cost is manageable, it's not higher compared to flash. Of course, when I talk about memory itself, DRAM, in DRAM the capacity even much lower, access time is even much lower, and the cost is much higher. Remember that we said that when you are designing storage systems, you have 3 aspects: capacity, latency and cost. Okay. You can usually have only 2 at a time, you can't get all 3. Okay. So again we have to figure out what has to be done. Let us just quickly look at what is the way we can try to exploit the characteristics to our advantage. So if you look at flash, for example, you can read about, to read one page, let's say one page is 4 kilobytes, 15 microseconds. This is much better than, for disk it is 5 to 10 milliseconds, because it includes C computational means. So this guy is really bad, disk compared to. Because of this, you can essentially do about 20,000 random 4 kilobyte transfer per second. Okay. Now it turns out, if you take any SSD, solid state disk, you have multiple channels. Okay. There is multiple independent units within a same SSD, so that you can essentially multiply by the number of channels, you will get that much number of IO operations. These are called IO operations because typically in database, you have to update 4 kilobyte chunks typically. This is your record, for example, your bank account record will be some small amount, 4 kilobytes, whatever, right? Because it basically has to have information about your current account balance and other things, not much. So usually small numbers, okay? So the number of transactions, it depends on number of 4 kilobyte chunks you actually can update. So if you are able to do 50 microseconds per 4 kilobyte and you can do 20,000 random 4 kilobyte transfers, that's IO operations. If you have so many k number of channels, you multiply by k of 20,000. And typically you can easily get 8 channels, 8 things of that kind, okay, 4 to 8 without trouble, 16 also, okay, easy, okay, depending on whether it is what's called enterprise SSD or consumer SSD. Consumer SSDs don't have too many channels because every channel incorporates, they are independently operated. That means that you need independent electronics for all this, okay. So for enterprise flash, you can go much higher. People routinely talk about 1 million IOPS per. In some of the more, let us say, expensive SSD devices, you can get that much, okay. So what is important about this is that IOPS are cheap here. Getting IOPS is cheap. What is costly? The capacity cost, okay. Compared to a disk, the capacity cost is high, but IOPS are cheap, okay. So you can, as mentioned, you can scale IOPS by adding more interfaces, planes and other things. So IOPS are cheap. And what is also important is that very high IOPS are required only in most demanding large applications. Typically most applications that we deal with don't require that kind of IOPS. So it's only specialty systems that require very high IOPS. Okay. A good example is some web service, for example. Suppose there is a World Football or Cricinfo, those kind of sites. There are thousands of people or millions of people accessing it. Then for those kind of guys, they have a very high rate at which information is pulled out. Okay. For them, IOPS is important. Unless you are one of those very big sites, eBay, Google, Yahoo, okay, Cricinfo, World Cup, football, all those kind of places, you don't have to worry about IOPS. Most of the systems can handle IOPS. Okay. So, okay. So basically what the important thing you have to remember about flash is that the cost per page is a more important parameter than cost per IOPS. Let's put it that way. In the case of disk tape, all those things, it turns out because it's 5 to 10 milliseconds for 4 kilobyte, you can at the most do 100 to 200 random 4 kilobyte transfer per second. So it is IOP limited. So if you are talking about some eBay kind of system, if they want to satisfy some 10,000 requests per second, a disk cannot do it, one disk cannot do it. You need to have, suppose you want to support 10,000 accesses per second. So you have, let's say, 100 4 kilobyte transfer per second is happening, let us say. That means you need at least to have 100 disks that are working concurrently. Then they can get to that kind of thing. So your IOP limited. So the only way to scale this is by putting more disks and tapes. You scale both the capacity as well as IOPS. Okay. So the cost is proportional to required IOPS. As I told you, if you are an eBay kind of system and somebody tells you that I have to handle 1 million IOPS per second, okay, that means that you have to have 10 to the power of 4 disks. There is no choice. You have to say, if you are going to be disk based system, you have to have about 10,000 disks with you, then only you can handle it, otherwise you can't handle it. That increases the cost tremendously. It increases power, it increases space requirements, all those things. Okay, that is where flash actually has benefited a lot. Basically, if you put a flash there, it handles the IOP requirement quite well under with low capacity itself. So for big capacity, you put in the disks. So given that, the question for us is, how do we figure out how much of this flash should be there, how much should be disk, how much should be tape? We will only look at the flash and memory, flash and tape issue. The tape issue will disregard for the time being because tape is essentially only for backup nowadays. It's not being used for anything else. Okay. So this is where the tiering concept comes in. Okay. You have memory, SSD, disk and tape. So what is the basic idea? I think most of you are familiar with this. You cache important stuff in more expensive memory and evict it to slower layer when they are not needed. Keep the more important stuff in the high speed memory if possible, wherever it is possible. Whenever you cannot keep it around because there is a contending request to store that place in that high speed memory, you push that unfortunate guy out to the slower memory, right? And then you can migrate up also. Sometimes what you push down to slower layer, it may be accessed again, so it has to be migrated. You can either migrate it in stages from one to another. For example, you move from disk to SSD to memory, or you can directly go from disk to memory. It depends on your system. Of course, if you go step by step, it's more latency and cheaper possibly, but if you go from disk to memory, it's faster but costly system. Basic for us is, how do we decide what is the cost benefit? How do we do these things? Okay. So this is a slightly tricky and subtle issue, so we'll just try to understand it carefully. Suppose we written a new 4 kilobyte page. Why is that happening? And you have an application. An application is generating pages all the time, new information. The application is writing something, is computing something, right? Now, if you compute a page, you have to store it in memory. Typically in DRAM, it has to be stored first. Okay. Now, it may be temporary memory. After a few minutes of time, it may no longer be necessary. It can be thrown on the floor. Or I compute something, I need it for some time later, much later. Okay. So either we keep it in memory, or after some time we write to disk. Because why do you want to write to disk? Because you want to reuse that memory locations again for something new I am computing. Okay. Because every so often I am computing new things. So now let's look at what are our options. Let's look at I sometime back bought 4 GB of DDR3. What is DDR3? Essentially, it's a type of DRAM with multiple channels. Okay, so that means there are, let's say, 2 channels. That means that I can independently access either this part of the memory or this part of the memory. Okay, that in some sense I can have 2 requests going on at the same time. So you can have multiple channel systems. DDR3 is a multi-channel system. So you have multiple CPUs, multiple cores, they can be pumping the memory simultaneously. Okay. So 4 GB DDR3 I bought some 1 year back, I think, for rupees 1200. That means that 4 kilobytes approximately this much. Okay. 1200 rupees by 10 to the power of 6, right? Because 4 kilobyte, it's 4 kilobyte and 4 gigabytes, a factor of 1 million away. Okay. This amount. Okay. Let's call it also C cost memory. C underscore M is cost of memory. Disk is, you can get a 1 terabyte disk nowadays for 5000 rupees. Of course, if you are using what is called enterprise disks, these are consumer disks. Enterprise disk will be about a factor of 2 to 3 times more expensive. Okay. We'll just use the, I think I should use the enterprise disks here because mostly I am talking enterprise disks, but anyway, I have used the consumer grade devices here. Just have to multiply a factor of 2, whatever I am talking about, if you want to go for enterprise disks. Enterprise disk is basically more reliable, better disk, okay, compared to consumer grade disks. Okay. For example, in a consumer grade disk, if something, it dies, okay, you lose your data, it's of course great loss, but you don't lose information like your bank account information, all this kind of stuff. Okay. That's why they can, it generally believe that enterprise should be much more higher quality than consumer devices. So disk is 5000 per terabyte for 100 IOPS. So if you think in terms, as mentioned, we are IOP limited. What is our costly resource? IOP, not space. Okay. So that means that I am paying rupees 5,000 for 100 IOPS. If somebody wanted 200 IOPS, I have to pay two devices, 2 disks I have to buy. This because I cannot supply it with 1 disk. At the most I can supply 100 IOPS. Somebody wants 200 IOPS, there is absolutely no way to do it with that. I have to get 2 disks, then only I can do it. So my cost is proportional to IOPS. Okay, that means it is rupees 50 per IOP per second. Okay, let's call it C underscore IOP. This is the cost per IOP per second. Okay, so if this is the cost, then it may be that I don't need IOP per second kind of cost, I need IOP per k seconds. Okay, that means the cost will be rupees 50 by k. That is, instead of doing it in 1 second, okay, this is basically per second cost, rupees 50 per IOP per second. Okay, if I don't want to do it in that smaller time, I want to do it much, I want to elongate for, okay, because I can work with even slower devices, let us say. Okay, so for IOP per k seconds, cost will be proportionally less, 50 by k. The question for us is, because I have to write to the disk, right? That means that the cost is just about the same when if you take this cost of that 4 kilobyte, if it is about the same cost, if I am going to write once every k seconds, okay, because I need to get a disk of that IOP rating, okay. So these costs are about the same when 50 by k is equal to the cost of 4 kilobyte, this one, okay. So this is some kind of break even at this point. So if you calculate it, it's basically, if you are in the using symbols only, it's basically k will be equal to C underscore m equal to C IOPS by k. So k will be equal to C IOP by C underscore m. Now if you look at these numbers, it turns out if you calculate for k, it is 4 into 10 to the power 4 seconds, approximately 11 hours, 4 kilobytes. If you do it for 8 kilobytes, it is 5.5 hours. What does it mean? It means that if you have generated some piece of information, if you want the cost of the IOP cost you are paying compared to the memory cost per 4 kilobyte you are paying, the costs are equivalent only if you store the data you generate for 11 hours approximately. Okay. So if some information is needed, I compute something and it's needed after 11 hours, then I should put into disk. If I am going to generate some information, I need it within the first 11 hours, then I should keep it in memory. Okay. Now this is a slightly tricky thing here. Why? Because that means that I generate stuff, I have to keep stuff what I generate in 11 hours in memory, in DRAM. In 11 hours I will generate amazing amounts of temporary and other data. I have to keep it around for 11 hours. That means my DRAM requirement is very, very high, extremely high. Okay. That is one of the reasons also you will see that nowadays most laptops etc. are putting more and more DRAM, precisely because if you want to have your system respond quickly, you have to keep more stuff in memory. Okay. Now if you take into account, let us say, let us add SSD. Okay. Basically what I am saying, since we have to keep data in memory for long periods, 11 hours etc., we need large memory. Okay. That makes the system very expensive. But notice that in the mid-80s, it turned out that disk was much more expensive, RAM was even more expensive, because for example, in those days it was $2,000 per IOP, something like that, and RAM was $5. And if you do the break even for 1 kilobyte, in those days 1 kilobyte was often the block size, it was 400 seconds. That means that you kept stuff in memory of 400 seconds, which is about approximately how much? About 6.5 minutes. So if you access something beyond 6.5 minutes, then you will keep it in disk, otherwise you keep it in memory. That means you need to store what is generated every 6.5 minutes approximately, okay, in DRAM in those days, okay. Whereas in our case it is 5.5 hours, whatever is generated in 5.5 hours. And notice also that those CPUs were slower, so the amount of data generated is going to be smaller. Whereas in 5.5 hours, our machines now with so many gigahertz and so many cores, they will be generating tremendous amount of memory data that they have generated, right. Some of it is temporary, they get dropped, some are temporary things which need not be stored across, okay, but still a good portion of it has to be stored. That basically means that in those days things were slightly more balanced. The disk memory was slightly more reasonable, not balanced, but there was some semblance of balance. Nowadays it's totally out of whack, completely out of whack, okay, because you have to have such a big memory to keep things, when only you will find that disk system is actually makes sense, okay. So because of this, you can start thinking about, can you put in some intermediate kind of device? That is what we can do is eSSD, okay, enterprise SSD. If you put it to, what will happen is that you will find that you are talking about some rupees 12,500 for 20,000 IOPS. It is about only rupees 0.62 per IOP. Previously, what was the number? It was rupees 50 per IOP, okay. This is very expensive compared to 62 paise per IOP. Okay. You can see there is a tremendous difference in the cost, okay. So if you calculate the same thing, break even between DRAM and ESD, it turns out to be 500 seconds. How am I calculating break even? I am using the same formula here, sorry. So what is the break even? C IOP by CM, okay. So if I do that, I put 0.62 divided by CM is what? This much, 1.2 to the power, okay. If I do that, it turns out, it comes out to 500 seconds, approximately 8 minutes. What is the difference? Because you now have to store approximately what you have generated, your CPUs have generated, about what is 8 minutes. That is all the storage, that is all the memory, DRAM memory required. So, need much smaller amount of DRAM memory, 8 minutes versus 4.5 hours. And doing everything for 8 kilobytes. So, basically this was 11 hours for 4 kilobytes, but it is 5.5 for 8 kilobytes, okay, if you calculate those things. That means that you can reduce your DRAM requirement dramatically if you have SSD, okay. That is the reason why you will see that a lot of people are playing around with SSDs. This is at the between DRAM and SSD. Now there is a corresponding thing that can do between eSSD and HDD. So what you have done is you have memory followed by SSD followed by hard disk. So between DRAM and SSD, this is the situation. Between SSD and HDD, it turns out the break even is 70 hours. Even this also is tremendous. One can imagine putting even more, one more layer. So people are talking about, I mentioned earlier, you have what is called single level cell SSD, and then you have multiple level cell SSD, and basically you can use this kind of additional layers. Then you can start finding that the amount of stuff that you need. For example, what this means is that you need a fairly big SSD, because that SSD has to absorb all the writes for 70 hours, okay. So you might find that by adding one more layer, probably you can reduce it to some more management, okay, because the more is bigger the SSD, the more costly it is, okay. So I hope this is clear. So actually people have started because of the obvious advantages of this kind of systems, because you can see the tremendous difference, okay. People have tried to see what they can do with this kind of systems, and what I mentioned earlier was that you can use the flash as a cache, okay. Basically what is the situation? Here what we are doing is, you have memory DRAM, SSD, what you do is you keep it as what is called a write through cache, okay. What is a write through cache? Write through cache means you write it to the cache and also it goes to the slower area also. That means there are 2 copies, okay. Because there are 2 copies, even if one copy fails, you can pick it from the other one. In write back, there is a single copy only, okay. So if you use the write through cache, what happens is, then you can essentially not worry if the flash fails, okay. And that is how people have been using for quite some time. For example, if you look at NetApp and other companies, they have a flash, what they call a flash cache, and these flash caches are quite big. They are about minimum 1 terabyte, 2 terabyte, 8 terabyte kind of systems. Okay. So if you use that flash cache, it turns out that for the reasons we discussed earlier, right, basically you can essentially match each of those layers, okay, instead of it being so totally out of whack, right, we can essentially match it better. And people also discovered, have actually experimented with this kind of systems. For example, there is what's called a benchmark, okay, from some organization called SPEC, and they were using a particular benchmark, and it turns out to get the kind of IOPS, because they are talking about this particular benchmark actually measures throughput, number of operations per second versus response time. Okay. So operations are very important, the throughput, how many operations you do. Okay. For getting the kind of operations you require, the only way to do it is by scaling the number of devices, scaling the number of drives, what is called fiber channel drives. The fiber channel drives are the most expensive kind of disks, and they usually run at 15,000 RPM. You look at the previous one, right? We are talking about, this is a consumer grade disk with 5400 RPM. So fiber channel drives typically run at 1500 RPM. So they are 3 times better. That means that guy is about 12 milliseconds seek average. That guy will be a factor about 3 times slower. That means 4 milliseconds. Okay. So he is able, because it's 4 milliseconds, he is able to do about 250. He can do about 250 IOPS per second. Okay. And you are paying about a factor about 10 times the cost, I think, approximately. Okay. And your IOPS has just increased from 100 to 250, that's all, nothing more than that. Okay. So, so if you really want to get the kind of throughput that you want, operation, okay, the only way to do it is by increasing the number of devices. Okay. So if you go to 224 drives, you get the desired throughput versus response time in this case. Okay. And you get, it turns out, because the fiber channel drives come with a particular size, if you increase the number of drives for the kind of IOPS required, corresponding the disk size also, the total capacity increases, it goes to already 64 terabytes. Okay. And take that kind of system, you compare with the system with only 1/4 the number, 56 fiber channel drives, but with a flash cache with 16 terabytes. Okay. Now this flash cache probably be about 1 terabyte or 2 terabyte. Okay. If you go with this kind of flash cache, even it could even be 512 gigabytes. Okay, it might work out. Depending on application, it might work out. That is just sufficient. Okay. We find that the performance is about the same. What's very interesting is that it's about half the cost, you include all the costs. Okay, because I mentioned to you that you're using flash cache. Flash is expensive. Okay. Even if you take into account the cost of the flash, because of the reduction from 224 devices to 56 drives, that cuts down the cost quite a bit. Even if you add the cost of the flash, in spite of all these things, it turns out the cost is about half. Okay. And you get about, most important, 2/3 power savings. Okay. Why is that? Basically, if you look at this 224 fiber channel drives, you're basically talking about something like about 10 to 15 watts per drive. Okay. And if you're talking about, if you take 15 drives for example, that means it's about approximately 4000 kilowatts, and I think you know about something called power factor. So it's 400 kilowatts, it becomes approximately possibly 600 kilovolt ampere. Okay. And so basically you are talking about a fairly big power system for this. Okay. And whereas if you go with this, you will be with a much smaller, probably 1 kilovolt ampere kind of system. Okay. So power savings is there. More important is space savings also there. Because just imagine storing 224 fiber channel drives. Okay. So there is a big aspect relating to the space requirement also, and that's why you will notice that if people are building very big systems, let's say somebody says that I have to devise a system with 1 petabyte per second bandwidth. How much? Some people are starting to think about all these things now. Okay, so for example, like let's not go with 1 terabyte per second, or we'll say if you say 1 terabyte or 1 petabyte per second kind of systems. These are very big systems. Okay, we'll just take the simpler of 1 terabyte per system. So how many disks are required for this? You will find that the number of disks required will be, because typically you get about, I told you, 800 megabyte per second approximately, maximum you can get. So if you do this, you will have about approximately 1000 or more. Okay, whereas of course it's 1 petabyte, it will be 1 million disks. If you put 1 million disks, what will be the situation? You will get multiply by 10. What is the power required? Is 10 megawatt. Now this looks like a minor number, but actually 10 megawatts you have to cool it also. That means you need air conditioning also. So you add the air conditioning, because the air conditioning also requires power. You add all those power for air conditioning, all this stuff, it turns out to be not 10 megawatt, it will be some multiples of 10 megawatts, 20 megawatts sometimes. You need that kind of a power to run this. Okay. Now 1 terabyte per system is very big, fine. Okay. But the thing is, you can essentially get the same thing with SSDs with not too much. It's very costlier, but you will not have to invest in a power plant. Okay. For example, if 1 terabyte per second, right? How will we get this? Your bandwidth, your SSD will be some kind of semiconductor memory. It will be approximately giving you about easily about 5 gigabyte per second kind of bandwidth you can get with multiple interfaces and other things. Okay. So, and if you, so the number of devices you need, okay, if you calculate it, it will be about let's say we said 1 terabyte per second. Basically you need about 200 SSDs, and each SSD will be about consuming power about I don't recollect right now, it will be in the tens of watts, multiple tens of watts, because SSD not everything is being used. Okay, you can not you can only pump that part of it which is being used. So you are talking about something which will be at the most kilovolt ampere, okay, not megawatts. Okay. So this is something that people have to think about when you are designing very large scale systems. Okay. So there is power savings and space savings, and so for large systems it is almost inevitable nowadays. So but the important thing is to remember how to think about it, how to tier it. Okay. So I gave you some outlines of a method, and this was first done by Jim Gray. Okay. Jim Gray was he got a Turing Award some time back, and he basically came with this what is called 5-minute rule. Okay. So in those days it was this 400 seconds I told you, right, in those days in 1980s, this is approximately, it's at 6.5 minutes, but the rule is called 5-minute rule. That means in those days the thumb rule was you keep some stuff, if the interreference interval is less than 5 minutes, keep it in memory. If it is more than that, put it in disk. Okay. So this kind of 5-minute rules updated to the current systems, okay, current system speeds, that's what you have to do. Okay. So if you do that, then your system will be reasonably well balanced and you will have a more cost effective system. Okay. So so basically in summary, tiering is an important trend in storage systems, and it is going to become much more important in the future, because you are going to have different types of storage available, and you basically have to be careful with respect to the sizing of each of these components, then you will get essentially a well balanced system. Okay. And the reason why this is important is because you will find that different technologies progress in at different rates. semiconductor technology that's there in DRAM, that's there in flash, that will be there in what is feature called phase change memory or racetrack memory. They will go at a particular rate, whereas magnetic medium will have its own rate. Okay, and now they are doing different things. If you look at the semiconductor memory, they are going towards access time optimization, and the magnetic memory they are going towards capacity. So they will be finally they will be going different ways. So finally you have to put some intermediate technologies which will actually which will somehow bridge the gap. So you will have intermediate technologies, many of them, which will all fill the gap so that there is a better balance. Okay, with that I will conclude today's talk, and we will continue this class on some other interesting aspects of storage design. Thank you.